Hello, I'm Dan Andersen with ISU Extension and Outreach, and today I'm going to be talking about anaerobic digestion of manures and agricultural residues, especially as it relates to carbon. So, first off, what is anaerobic digestion? So, it's a process where we can take residues, oftentimes it's been manures, agricultural residues, but almost anything that's an organic material can be anaerobically digested. Uh, it's going to be filled with pathogens and macronutrients, lots of unstable organic material, and it's really that unstable organic material that we want because during the digestion process, that's what gets converted into our end product of methane. We throw it into a tank, and a consortium of microorganisms go to town, eating it up and converting it into different compounds, the most important of which to us is methane. And on the outside, we hopefully generate a treated effluent on this. Most of the research has shown that coming out, it's relatively low pathogen, sort of like composting. As you consume that organic matter, we tend to kill off some of those pathogenic things, which is good. It's relatively nutrient rich. Of course, that depends a little bit on how nutrient rich it was to start with. It generally is a nutrient conservative process, so all the nitrogen, phosphorus, and potassium we start with will come out the other end, but we won't make any new nitrogen, phosphorus, or potassium to add. And then the other big advantage is it's relatively stable. And by stable, I basically mean that those things that cause odors, that decaying carbon that often leads to smells that are unpleasant, has been broken down and converted into CO2 and methane, both of which are odorless, and results into a relatively low odor product. Now, it's not odorless because there are compounds in it like hydrogen sulfide, ammonia that will present some odors, and in certain situations we might want to do something with that, but it generally is much less odorous than when we started, or at least than the potential it would have to cause odors while it was stored. Now, you might say, why would we do this? And certainly a lot of the history of anaerobic digestion is just that, because we want to provide treatment. So, for instance, many municipalities will use anaerobic treatment, at least in part, for some of their wastewaters. But from a carbon cycling perspective, and one of the reasons that anaerobic digestion of manures and other agricultural residues has been pursued so often is because we can also make energy in the process. And that energy is in the form of methane. We can do a couple things with that methane, right? We can burn it through a generator to make electricity, and that would be a renewable electricity since we're no longer mining carbon from the ground that we have to combust to make that process. It's a renewable form of fuel. We can also combust that just to make heat energy. And then finally, the newer reason that it's really started to catch on is compressed natural gas that gets put in the pipeline and rather than burnt on site is combusted by some process user downstream. In the aspects of making this, we're also going to make some carbon dioxide. Most digesters make roughly 50% methane, 50% carbon dioxide as they break things down. So when we talk about low carbon fuels, one of the things we're trying to do is eliminate that carbon dioxide emission. Most of the time when we do that, it's a concern to us because we're digging up this carbon that's been stored underground in the form of petroleum or coal or natural gas for years and years, and all of a sudden, when we combust that, we release it to the atmosphere. In this case, that carbon dioxide that we're releasing has recently been cycling, right? It was in the atmosphere, it went into plant matter, we fed it to an animal, it became manure, or it was recently in that atmosphere, became plant material, and we put that plant material in the anaerobic digester. So it's what we'd call biogenic carbon, not new carbon that has been freed to be a part of the carbon cycle, but that's already actively cycling. Of course, there is some interest in doing other things with that carbon dioxide, whether it be finding value-added markets, putting it in a pipeline and sending it to stable locations in the United States for storage long term. How that ends up really remains to be seen, but doing something with that carbon rather than releasing it to the atmosphere, which is what we typically do right now, does have the opportunity to alter the carbon intensity scores of anaerobic digestion. And when we talk about the global warming potential of different fuels, that carbon intensity score really becomes important, and it's often a metric by which those anaerobic digestion companies really get paid for the value of their fuel. I did mention it does make a few other things. One of those is H2S, hydrogen sulfide. Hydrogen sulfide has that rotten egg smell that you might characterize with natural gas. Normally with true natural gas that we're buying, that's been mercaptan that is added. Here it does have hydrogen sulfide, so it would naturally smell that way. But most of the time we're running it through some sort of treatment process to remove that from the gas stream because when we combust it, it can cause unfortunate side effects in our generator where we end up making sulfuric acid because it's not exactly like mercaptan sort of in properties. The anaerobic digestion and treatment process, I have it diagrammed here on the right, and it's really a flow from the stuff we start with. And those things probably look pretty familiar to you if you think about human diets, right? It's carbohydrates, fats, and proteins. And the microbiology of our treatment system is going to take those, break them down, and turn them into various process chemicals along the way. Free fatty acids, and then finally down into short-chain fatty acids. Short-chain fatty acids are things like vinegar, right? So things that we're relatively familiar with. And then finally in that last step, our methanogens will break down that vinegar and make a molecule of CO2 and a molecule of methane, right? And that's roughly why it's 50-50 when you think of roughly the percents we're going to make. It can vary a little bit depending on sort of those things that we start with. If we have more fats, we tend to be more methane rich. If we have more carbohydrates, we tend to be more CO2 rich in our gas. But it really is just a process of these are the things we fed it to start with, and because of that, we can end up making these things. One thing that's unique to anaerobic digestion compared to maybe other fermentation processes that you might be familiar with, such as ethanol production for either beer brewing, or for generation of fuels, is that we use a consortium of microbiology, right? So it's all of these different types of bacteria that really make that process happen. When we're making ethanol, we really want to start with clean stuff, clean material, clean tanks, and seed it with very specific bacteria. So this is what I would call a dirty process, right? It doesn't have to be clean. We still end up with the right microbiology present to make that methane, which is our goal. How good of a job we do converting is really dependent on sort of how many volatile solids we start, how degradable they are, and then the temperature and time that we give things to react. So if we start with things that are really lignin rich, like wood, we probably won't break it down very well. If we start with something like sugar water, right, where it's really easy to break down because it's filled with carbohydrates, we'll have a much higher biodegradability and get a greater percent of that carbon molecule to turn into methane. So every material really falls on a spectrum somewhere between what I would say is wood and what is that sugar water. And it varies from material to material. So one of the things that we have to do when we start thinking about anaerobic treatment processes, sort of characterize that material. Now, there are a few processing advantages to anaerobic digestion, and the first one to me is that non-sterile reaction vessel. And that's a big advantage because things like manure are never going to really be sterile. They'll never be clean. And being able to have a non-sterile reaction vessel, a non-sterile process, really is an advantage to us because it allows us to do this sort of processing and not have to worry about it, right? We're going to end up at the right end products. A second one is we get automatic product separation. So with ethanol, right, we have to do something like steam distillation. If you drive by an ethanol facility, you'll see those large columns on the outside where they're doing that. And it takes some energy, it takes some sophistication really to get product separation. Here, since we're making a gas, methane, and it's relatively insoluble in liquid, right, it automatically bubbles up and we'll get a gas headspace above our liquid in our digester. So we get that automatic product separation. Now, that gas isn't perfectly clean, right? It has a lot of methane in it, a lot of CO2, small amounts of other things like ammonia, water vapor, hydrogen sulfide, and probably some diatomic nitrogen. So we do have to do some additional cleanup oftentimes. But at least from getting it out of the liquid perspective, it happens for us automatically. The other thing that's a huge advantage is it's a relatively simple piece of equipment and a relatively simple operation. Now, certainly we can make it more sophisticated, but really it is as simple as most of the time putting this organic material in a tank, getting rid of the oxygen, and just giving it time to react. The real question has been can it find a competitive economic market, right? Can it compete with compressed natural gas? Can it compete with electricity and be profitable? And that's been the challenges we've seen anaerobic digestion before. We looked at it in the 70s. We looked at it in the early 2000s. In the 70s, it was a result of high energy prices, and we thought, oh, here's a chance to be renewable, a chance to compete. And then very shortly after that, energy prices came down. In the early 2000s, we saw the advantages of new generators being built, often microturbines that were more efficient, and it gave us some opportunities. But again, that boom didn't really stick around as the price of other renewable fuels, such as wind and solar panels, really came down and became probably a bigger opportunity than compressed natural gas for that electricity production. This time it's a little bit different because we've seen the development of different carbon markets, right? Through either D3 RINs, where we're looking for cellulosic fuels, through low carbon fuel standards, where we're rewarding something for how much carbon intensity or sort of that greenhouse gas potential it's removing by this advanced processing technology. Of course, it does have disadvantages as well, right? And the big ones to me are it has relatively slow reaction rates, and we'll talk about this in a little bit more detail. But oftentimes when we think about making ethanol from corn grain, we might be thinking about reaction times on the order of magnitude of hours, right? We might do a batch in 12 hours. With anaerobic digestion, we often talk about reaction times in terms of days. So I would think 20 to 60 day hydraulic retention times, solid retention times in my reactors. And what that really means is since we have slow reaction rates, we have to build big tanks to make these processes happen. So other technologies like that ethanol production are really scalable because we can do lots of batches and we can end up with a little bit smaller plants, whereas when we look at anaerobic digestion, since it is slow, we need these big tanks and oftentimes that takes up a little bit more space. Another disadvantage can be relatively low methane yields. And low is sort of a relative word, right? Because we can have different reactors that can make what I would say higher amounts of methane, but still when you compare them per cubic foot of reactor volume and compare it to something like ethanol, we're making a lot less methane energy per reaction vessel volume per day. That isn't necessarily a unsurmountable challenge. It's just something that, again, ends up with bigger tanks and some bigger initial costs as we sort of size that facility. And then the other thing is we are turning that sulfur into hydrogen sulfide. Hydrogen sulfide can be a dangerous gas. As I mentioned, as we combust this gas, it can cause things like sulfuric acid, which cause some rusting and corrosion. The good news is we've came up with a lot better technologies to remove that sulfur from the gas. So the price of that treatment has really come down over the last 10, 20 years. And it's really become pretty standard to remove sulfur from almost all our biogas that we make because it's necessary for almost every process. So we've really seen improvements in that area. When we size digesters, one of the first things we want to know is really how much product are we going to make? And there's a few ways to do that. The big test that most people use is the biochemical methane potential test. Really, you take a substrate, a small amount of it, let it react in a lab where you've inoculated it with those right types of bacteria, break it down for an extended periods of time and see how much methane it makes. For the world of livestock, we've done this with lots of different types of manures, and we know that it's proportional to how many volatile solids or organic matter we have in our manure and what we feed our animals. So there's some data on here, and you can see that swine is different than dairy, and really that's a breakdown of how we feed things, what we feed things. Swine are fed high concentrate diets. That stuff is very digestible. The pigs do a great job of digesting it, but even what comes out is relatively digestible. On that dairy one, even though I have it labeled as a concentrate diet, we end up feeding dairies a relatively high amount of forage, especially compared to pigs. That forage has some lignin, and anaerobic digestion just isn't a technology to break down that lignin. But if you have a biochemical methane potential, you can get a first estimate of how much methane we think we can make from any substrate. Scientists are still in the realm of doing a lot of these tests for different things that we might want to run through an anaerobic digester, whether that be corn stover or sorghum or cereal rye cover crop that we've harvested. So there's a lot of investigation going in to what are some potential options, how much methane can they really make per unit of volatile solids, and then again per how much material we're feeding that digester, because that's really what helps make a project here work, right? If we can find materials that have more methane potential that are relatively low cost for us to purchase, it gives us a good chance, a good opportunity to make some money breaking that down and turning it into an energy project. My work there was all talking about per unit of volatile solids. That's how we've normally done it. There are some instances where people work off chemical oxygen demand because chemical oxygen demand is really easy to test. In my lab, I can measure chemical oxygen demand in roughly 4 hours. Running a biochemical methane potential will take me something like 35 days. So if you want to screen materials to say, is this even feasible to make a digestion project, we'll often start with chemical oxygen demand because it goes quick and easy and at least tells us if we're in the realm of possibility. When you use chemical oxygen demand, you do need an efficiency. How much of that chemical oxygen demand are we going to break down during digestion? There's some different estimates for different types of materials. For manures, I often use in the neighborhood of 50%. It works out relatively close from some design experience we have. When you switch to lignocellulosic materials, other materials where we don't have as much experience, estimating that number gets a little bit more difficult, but we do tend to have some design guidance out there. So for really lignin-rich materials, we're probably in the neighborhood of 30%. If we're feeding something like sorghum silage, like we'd feed to cattle, we're probably really close to that 50%, maybe even 60% chemical oxygen demand breakdown during the digester, because it's something that hasn't been pre-digested by an animal, so it can be better than manure. In this case, I just have a little example to walk through sort of how we might estimate how much methane we might have for a potential project. So here I have a swine finishing farm. They make 4,000 gallons of manure a day, so I probably have about 4,000 pigs on that farm. Swine manure, in this case, I said it's going to have a COD of 20,000 milligrams per liter. Depending on your management system, you might find manures with up to 100,000 milligrams per liter, right? So there's a large variation sort of depending on how that material has been managed beforehand. We'll probably break down roughly 50% of that material. The one rule of thumb you need to know is you get 6.3 cubic feet of methane for every pound of chemical oxygen demand you break down at 95 degrees, which is a rough temperature we'd be at for an anaerobic digestion. I'm going to do some unit conversions there because some of my stuff here is in metric units, so gallons to liters is roughly 15,000 liters. I'm breaking down half that chemical oxygen demand, so 150 million milligrams per day. That works out to about 331 pounds. So if you take that 331 times 6.3, I'll make 2,100 cubic feet of methane every day. If I wanted to know how much biogas that is, biogas from manures is generally about 60% methane. If we're doing a lot of other materials, I'd estimate closer to 50%. We'll end up making somewhere in the neighborhood of 3,500 cubic feet of biogas per day. And that's really how we'd size our digester. Now, we might put some more sophistication in it, but that tells me roughly how big my gas cleaning system is going to need to be, how much I'm going to be putting in the pipeline every day, right? And how much CO2 I'm going to be off-gassing from this process, which really is a big part of sort of the how do we design these things, how do we make them work. The other is sort of the size of the tank, and really that is based on hydraulic retention time. And generally we'll size a hydraulic retention time, a solids retention time, for most practical digesters in the agricultural spectrum. Our hydraulic retention time or solids retention time is the same. So I'm going to just talk about hydraulic retention time. If you have really unique situations, we can come up with more sophisticated designs that separate those two, because we really want a big solids retention time, and it'd be okay to have a shorter hydraulic retention time. But that adds a lot of sophistication, oftentimes cost, and challenges to management. But that hydraulic retention time tells us how much stuff we really need to store, right? So for manure digesters, we're typically in that 25 to 30 day hydraulic retention time. If I'm digesting lignocellulose materials, crop residues, I'll probably be longer than that, somewhere around 40, maybe even up to 60 days, depending on how hard it is to break that material down. On the other hand, if I put an anaerobic digester to help Pepsi or Coke with their sugar water residue that comes out of some of their processes, I might need only a really short hydraulic retention time, somewhere in the neighborhood of 10 to 12 days. And that's the type of place where separating hydraulic and solids retention time really can be a huge advantage. So the hydraulic retention time, just to give you an idea of what it is really how big a tank do I have compared to how much I'm putting in and taking out every day. And that really is just how big do we need. And if I know how big a tank I need to build or buy, that really tells me the rest of my sizing and anaerobic digestion story, right? Because I'll know how big a tank I have. I can size my gas cleaning equipment from that chemical oxygen demand or biomethane potential that we already talked about. And that's really the basics of the two things to get you started on a process. So hydraulic retention time matters because it really is how long it's stored in the tank. And how long we store stuff can influence how well we develop that biomass, that microbial biomass, how active they are, how many of them are there. It can also influence things like their ability to interact with food, right? So if I have too many microbes and not enough food, I've sort of starved my system and I could probably add hydraulic loading. If I have too few microbes and too much food, well, it takes a long time for them to eat everything, and I could probably adjust it to save myself some money in that process. So really what we're trying to do is balance those two so we can consume it as quickly as possible, but still get a relatively high conversion rate of whatever we fed and get it broken down. In general, if we can design systems that have low hydraulic retention time, that saves us money because the tank is smaller, but we do often pay for that through adding sophistication and more challenging management to that tank we've built. I promised you I'd talk a little bit more about what some hydraulic retention times are. So that ethanol fermentation, that's what I have there on the top. We've optimized that to be a relatively fast process, somewhere in the neighborhood of 48 hours. If you think about making renewable diesel, right? So transesterification for biodiesel, that's about a 2-hour process, and you can shorten it a little more with ultrasound treatment of whatever we're turning into that biodiesel. On the other hand, when we move to anaerobic digestion with sugary wastewater, if I'm separating my hydraulic and solids retention time, I might be able to get that process done in 8 hours. If I move towards manures and other agricultural residues, I'm really looking more at that 20 to 60 day window, in some cases maybe even longer. And then there are various treatments that people are studying to try and speed that process up. I won't tell you that we have it figured out, but we do know that grinding things up, of course, makes the process go faster, and we're trying to balance how much do we have to grind to how much hydraulic retention time that improves us, and does it lower our overall carbon footprint? Does it change the process economics enough to justify doing it? So that is an active area of study for anaerobic digesters, and where people are still trying to make some improvements. We're going to go through just a couple of different types of anaerobic digesters. There's really two that dominate the market. The first one is a completely mixed digester. Really all this is a tank where we have feed coming in one side, that treated effluent coming out the other, and we'll have it stirred. So I show a propeller mixer in there. Oftentimes it's not mixed with propellers in practice. We might use pumps, but there are still sometimes we'll have some of those large impellers in there trying to mix things up. So one big advantage of these is they've been used a lot. So we have lots of experience at municipal wastewater treatment plants, at some production factories where they've used them before. So we really have good design guidance on how well they work. They work over a relatively wide range of solids contents, something from almost no solids up to about 10%. As we get to that 8 to 10% solids, it does get hard to keep it mixed. It gets a little harder to want to expend all the energy it takes to keep it mixed, so we might start switching to different digester types. But that's a relatively large range that encompasses a lot of manures, especially things like swine or dairy manure, and it can work with both flush or scrape systems because of that. As we think about agricultural residue digesters that use corn stover or sorghum silage, these digesters can be used, but we'll oftentimes have to add a fair amount of water to make that process feasible, to try and get them down into that neighborhood of 6 to 8% solids. Sometimes that's justified, especially if we do some separation on the back end and can recycle a lot of that water. Other times that might be more dilution water than we want to add, and we'll look to other types of systems. One thing that this system has as a disadvantage is that mechanical mixing requirement. It does require energy to do that. Most of the time we can be relatively low energy if we're sort of in this sweet spot for solids content of that 4 to maybe 8% range. When we get lower than that, oftentimes it's very watery, and we'll look for something like a fixed film digester, which I'm not going to talk about much because that tends to be something we see more for sugary waters and food processing rather than agricultural situations. And the other one is, in this situation, we aren't doing anything to help our biomass stay in that tank, right? So our bacteria are going to build up to a certain level, and then they outflow at about the speed that we're growing them. And unfortunately, that slows down our reaction rate some, but it does make the process relatively easy to manage and doesn't require other monitoring to really make it work. The second type of digester that we see a lot of is plug flow digesters. And this one doesn't have any mixing inside, at least it has minimal mixing inside. In some cases we might see transverse mixing sort of across the system rather than down the length of it. So this system, unlike the other one where whatever we put in, we assume that it gets evenly mixed throughout that digester relatively quickly. In this one, we're moving things sort of as a plug. So one example of a plug flow digester might be the human or the pig, right? It eats one day and it takes a few days for that food to work through our system and out. A plug flow digester is really the same way. That material is going to move through us from the front end of the system to the back end of the system. And as it does, the microbial biomass develops, breaks down, and then eventually we're done treating it in our digester. So if we compare sort of that plug flow digester to a completely mixed, from a scientific standpoint, plug flow digesters can get a higher conversion efficiency. They can turn more of that organic material into methane. at least in theory. In practice, for the most part, we see roughly the same performance of a plug flow digester and a completely mixed digester when we're optimizing it for methane production. If we were optimizing for treatment to hit lower levels of organic material coming out, we might be able to make that plug flow digester work better, but it really requires us to build bigger tanks, longer hydraulic retention times, and most of the time, that's not the goal that we've been chasing unless we're at that municipal wastewater treatment plant or some other rare situation. Again, these systems have a good track record. They've been in practice since the 70s, where we've had people using them. They work well with manures and biomass materials that are a little bit thicker in consistency. So oftentimes with scrape systems, if we have beef cattle systems, it's been very popular there. If we have dairy systems where we're minimizing the amount of wastewater that we're generating, either from washing our milk house or cleaning, or if we're pushing that material somewhere else rather than into our digester, plug flow digesters can again be a great option. Plug flow digesters, since they tend to not have that mixing, or at least as much mixing, do tend to require higher solids manures. That might sound a little counterintuitive at first, but by having that higher solids content, we can really get it to flow through more as a plug rather than just sort of flopping all over and having those solids settle to the bottom and never get resuspended. So that's the one fear we often have with plug flow digesters is stuff just settling to the bottom and settling out. Because of that, they really aren't compatible with sand bedding unless we're doing sand recovery before it goes into the digester. The bottom picture there, I have a plug flow digester you can look at where it hasn't went into use yet, right? The cover's not on top of it, so we can see what it looks like. What happens on that digester is on the end that's far away from us, on one side that's an inlet, the material will flow down towards us, have to turn the corner, and then it will flow back the other U and will pump out, right? So rather than making one long sort of plug flow digester, it's U-shaped in this case. It's still a plug flow digester, even though it's a little different than how we conceptually drew it up. And we'll oftentimes do that just because it helps us minimize heat loss in some cases. So digesters have been around a long time. They received a lot of attention in the 70s, the late 90s, early 2000s were another sort of era where we saw a lot of interest in them, but we haven't really seen them take off in the agricultural sector before. It's been hard to compete economically. Most of the time, historically, we've really been in that electricity market. It's only recently that technologies like pressure swing absorption have come around to help do some of the natural gas cleaning, scrubbing, to allow us to do things like put compressed natural gas on the pipeline. We've seen a lot more interested in carbon credits and carbon scoring. Certainly there was talk of a carbon market in those early 2000s, but we never really saw it develop. With the federal government supporting that RIN market, the renewable identification number for things made from cellulosic fuels, as well as certain states and Canada adding carbon intensity scoring and encouraging low carbon fuels, there's been opportunities to monetize that. The other challenge we've often faced is these things have to get relatively big before they become an economic option. In some cases, even as we've seen farm sizes grow, that often means we might think about adding biomass material to our manure to hit a bigger economy of scale. And part of the reason that we have to do that or might want to do that is there are some initial investments that are relatively large for these systems. When we size a tank for a, let's say, 20,000 head swine farm, we might be looking at the neighborhood of $2 million investment for that digester, another $2 million to sort of clean that gas to pipeline quality, and then probably $1 million to hook it up to a pipeline and inject. So those are relatively large expenditures, and to get enough value from this process to make that pay, we do need to make a fair amount of gas. Now, there are things we can do to sort of mitigate some of those struggles, right? We could find a plant near us that's already doing biogas injection and use trucks above ground to move our biogas to that injection point, and then other farms might be able to take advantage of this. So really it's something to pay attention to as that market develops, but there will be some scaling up challenges, at least as we first start and try and make these things work. If you're wondering what this might look like for a farm, this is just an example of how I might design a system, what I might be thinking at. I'd get all my manure sort of to those AD systems, run them through. I probably am going to add some silage bunkers, right, because I want to feed some biomass and at least if I'm at a smaller scale, silage makes a lot of sense. They go into that anaerobic digestion. We have them in there to be processed for somewhere in the neighborhood of 20 to 40 days. As they come out of the digester, I'm going to run it through a solid-liquid separation system, mostly because in order to optimize my carbon intensity scoring, I'm going to put that effluent that comes out into storage of some type, and I'll want to cover that storage so that I minimize any nitrogen loss from it, so it still is a great fertilizer, but also so that I can maximize my carbon intensity scoring for some of those value-added markets. That solid material probably goes to something that might look a little like a compost system. I'll probably have to turn it a little bit more to start with because it'll be fairly wet, so I'll use that compost for drying. And then at the end of the process, I'll have that liquid fertilizer that looks a lot like manure, maybe a little more homogeneous, probably, hopefully, since I put a cover on it, have a little bit more nitrogen in it. And then I'll have this compost product that, depending on the separation system I'm using, may have a little bit more phosphorus in it, but it really depends on what I've started with, what I'm using for a separation system. But I will have this organic material that I can haul back to some of those fields where I was hauling biomass from to make sure I'm maintaining my soil quality in those areas. We'll always have a flare on site, so even if we're doing gas treatment, putting it on the pipeline, in case that system's down for maintenance or we break something for a period of time, we will have a flare that can combust off any of that excess biogas we're making that we can't find a use for at this moment. Certainly we want to try and minimize that, but we will have some time periods for maintenance, and hopefully we'll have some storage in our digesters to manage that. But from a safety standpoint, it's something that I strongly encourage and generally should be required. Here's just a picture of the plant near Ames. This one's owned by Verbio. They are going to be digesting corn stover in their digesters. You can see they're in the back of the pictures. They have 8 there. They are doing solid liquid separation when it comes out. The liquid goes into their effluent pond there in the back, and it does get recycled and used with corn stover they're adding to the process. People are still trying to figure out what biomass materials might work. I think corn stover looks favorable in Iowa because we have lots of it. We're still doing some work to try and figure out what optimum pre-treatments might be, what sort of retention times, how fine should we grind it, but there's definitely work in that areas. A lot of other people, especially farms that have had manures, have looked towards sorghum. It can yield a little bit more biomass per acre. Of course, we don't make an additional crop generally, right? We're not making corn and then just harvesting the stover as a waste product, so there's some balances there. But we can ensile it. It mixes with manure relatively well, and definitely are some options. There's a few scales that you might see this implemented on, right? So if we start thinking farm scale, we might do relatively little biomass addition to our manure, and sorghum makes a lot of sense. If we're thinking about this process as sort of a biorefinery, something that's a little bit larger, it may in some cases be difficult to get enough of those alternative crops growing quickly that we might have to use some residues that we already have, like that corn stover. And in some cases, that corn stover might make the most sense to start with. There are some real challenges to getting this technology implemented. Pipeline connection tends to be expensive yet. Hopefully, as we see more people utilizing it, developing some technology in that area, those costs will come down. It also means that your distance from the pipeline, especially as we start, is really important. I think as this technology develops and grows, we'll see some opportunities to move biogas above ground. But for right now, most of the projects that have been implemented are relatively close to pipelines. One place that we still continue to see a lot of improvement is in that biogas cleaning. It does have to meet process standards, right, to be injected on the pipeline. Those vary depending on the pipeline that you're working with. In the Midwest, we generally want something that's 90 to 95% methane. Every pipeline is a little bit different. On the coast, sometimes they require higher standards for getting that biogas in the pipeline, and different cleaning technologies have different levels of methane purity that they're able to make. The good news is people are still actively improving these processes, and we've seen the cost drop pretty significantly for some of those biogas cleaning systems like pressure swing absorption. There are the other membrane systems that are being developed that show a lot of great promise for making that cost even lower for biogas cleaning. And as we think long term, continuing to bring sort of the capital cost for that cleaning system down, as well as the operation and management cost down, is a key for long-term success. These processes, especially where we think about it as a biorefinery, where we might be bringing in large amounts of biomass, we probably have to think about developing in a market for that residual digested biomass. There's a fair amount of the carbon material About half of it that we bring in hopefully gets broken down into CO2 and methane, but that means about half of it also has to have something else to do with it. Right now, that's mostly making a soil amendment product, something that can help us build some of our soil health, be returned and build some carbon in our soils. Thinking more long term, they are interested in trying to do other things with it. It is often a lignin rich material, and there are many scientists trying to come up with value added products for lignin. As I look at one of the challenges more specific to Iowa, where we've invested in deep pit storages, we have to think strategically about how are we going to get manure that pit to our digester on some relatively frequent basis, whether that be an on-farm digester. We might think about daily getting manure up. If we're thinking about pods of farms working with a single sort of community digester, it might be weekly or bi-weekly that we're moving manure from that deep pit to our digester. And you might say, well, we've done that for years, right? We use manure as a fertilizer all the time. We're really good at pumping out of pits. And I agree. The challenge here is really that in a 2-week window, I might only add an inch and a half of manure to my manure pit, right? So it's a relatively small change, and I don't have that much to pump out. So I have to do a better job of getting the residual manure there out of the barn to my digester. And it just adds a new challenge to pumping rather than working with pits that are relatively full. So I'm not saying it can't be done. I definitely believe it can be. I've seen some potential solutions for it already, but it is something where we have to think strategically about how it will change our current system. So with that, hopefully you got a nice introduction to what digesters are and aren't. They do offer a great opportunity for us to add value by processing carbon in meaningful ways while conserving all the fertilizer, the nitrogen, phosphorus, and potassium that we already have. If you do have any questions, you can see my contact information there, and I'd be happy to try and address them for you. Thank you.